Fantastic. Well, thank you very much for coming. It's fantastic to see so many people interested in computer architecture in one room. I get less people from my undergraduate lectures, unfortunately. I'd like to talk about some of the current... It's a super exciting time, actually, for computer architecture, and that's kind of obvious talking to people outside around lunch. So I'd just like to talk about some of the current challenges and opportunities, really, in computer architecture, and how we can perhaps innovate faster, which is one of the things that we've been thinking about with the lowRISC project. Before I start, I should acknowledge that everybody involved in this project, so I'm a very small part of it. Lots of people involved in lowRISC, and Alex and Gavin, the co-founders, are here today, as is Andy Hopper, who's been chairman and has always been super supportive of all the strange things I've tried to do when I've been in the lab. And also to my PhD students, who I've really been blessed over the years with fantastic PhD students. It's always really exciting when you give Cambridge PhD students, you throw them at a new problem, and when having somebody super bright take a new look at an old problem, and so many times this has bared fruit. And all my other collaborators and colleagues in the computer architecture group and the computer lab. So I think the story of computing is a really amazing one, and especially I think one of the things I sometimes think about is how simple a microprocessor is. And actually, when you look at modern machine learning, how simple the concepts, the ideas are at the heart of machine learning as well. And we often just end up doing very, very simple things very, very fast. But I think computer architecture keeps us on our toes. It's the problems, the applications that we want to run, and the underlying technology are continuing to evolve very rapidly. And that means that the trade-offs that we make have to keep changing. The machines that we build have to keep changing. And our intuition about what works often shifts a lot over time. It isn't valid for very long. So I had a go at trying to sort of illustrate how far we've come. Obviously, EDSAC, I think it would struggle to execute an LLM. I suspect that it wasn't reliable enough to stay active for thousands of years. And it's perhaps a little bit unfair on EDSAC because they probably would have been able to specialize it for a machine learning workload. But I still think they would have struggled to execute LLMs faster than in thousands of years. But of course, we've made incredibly rapid progress over the decades. It's just sort of unimaginable progress, very, very exciting. And then looking forward, so if we look forward to EDSAC plus 100 years, so sort of computer architecture 2049, are we going to be able to do 1 million times better? And I think that's a really exciting thought, and where we would be if we were able to do that. And I think it's exciting from a research perspective. It's also super exciting because computer architecture is at the heart of so many problems that we're trying to solve in the world today. So I think it's both exciting from an academic point of view and critical to so many areas. So I think one thing to remember is that at each stage, when people built these machines, everybody thought the next step was going to be impossible. And I think people tend to extrapolate in very simple ways and point out the wrong roadblocks with hindsight. And then similarly, they're very blinkered in terms of what needs to improve, and then we often just head off in a completely different direction. So I think this was the case in the 1960s, where people, I think, resisted parallel computing. In the 1990s, when people didn't want to make the shift to multi-core. And of course, people have been calling the end of Moore's law since 1964, when it was coined. So I think lesson one, don't be too pessimistic about scaling. I think there's still a huge way to go. Of course, many of you will say that parallel computing kind of makes the job easy. General purpose computing is much harder. And yes, we've really struggled to improve single thread performance. I think we have to be bold. So I think there's 3 possible routes to higher single thread performance. The one is, I think, to be bold and say that we've sort of maneuvered ourselves into a microarchitectural local minima. We've been very clever, and we've created lots of good level, realistic, understandable levels of abstraction and interfaces between hardware and software, but they're really looking very outdated now, and I think we have to be bold, dissolve these interfaces, and look for radically different approaches, completely refactor programs, which tend to be highly overspecified. I think the other way forward is just to innovate much faster. So computer architecture research tends to be quite slow, and I was thinking about some of the projects I've been involved in over the years. It's taken a decade to develop a small microarchitectural innovation, and I think we can perhaps look at ways of innovating much faster. As I say, I think there's also room at the top. So automatic algorithm level optimizations, really moving up the levels of abstraction and optimizing programs at a much higher level. Machine learning, I think, has been a gift for computer architects. So it's a really interesting, forgiving workload. It's embarrassingly parallel, really simple compute patterns that we can evaluate at compile time, highly flexible and forgiving. We can do all sorts of, for a given, there's a sort of infinite range of model architectures, optimizations we can make at the model level, lots of optimizations for code design. People have made huge leaps forward in quantization and specialization of hardware. This is from Bill Daly's excellent Hot Chips talk, where he talks about 1,000x improvements in inference performance over the last 10 years. So it's a really interesting workload, and it's sort of come at the right time, I think. So looking forward, I think there's lots of scope for improvement from where we are today. So industry at the moment is focused on building and training very large transformers, very large language models, and they're not really spending much time trying to optimize these models. It's too risky. So there's huge effort, enormous effort in training these large models, but I think there's an awful lot of efficiency left on the floor, and hopefully we'll come back to that and be able to build these models in a much more efficient way. And these new models that go beyond current transformers have already been proven at a smaller scale, so I think it's only a matter of time that we see them being used in larger models when the current sort of race perhaps gets more difficult, where it becomes more difficult to push forward just by sort of brute force approaches. The other thing I think will happen is we're able to distill large language model functionality into smaller specialist models, and these might be large language models in themselves, or they may be other forms of machine learning or more traditional computer science. And I think there's probably lots of efficiency gains there. Fundamentally, you're looking for more sort of sparsity of execution of the model. I think there's also further hardware specialization, system-level efficiencies when you think that people are executing a very large number of queries of different types at the same time, and also sharing compute sort of between the data center and what is an enormous amount of compute available at the edge. So I think it's super exciting times for computer architecture, lots of really interesting problems to solve. Technology, yes, has slowed, so I think we're only probably going to get maybe 2x, maybe a little bit more in terms of density improvements over the next year, and maybe only 2x in terms of flops per watt. But there's lots of interesting technologies beyond silicon. I was chatting to somebody outside about physics-inspired computing and optical computing, and of course, there are many interesting new devices that may replace the traditional silicon transistor, and many of these techniques offer perhaps an order of magnitude improvement in performance. I think it's perhaps going to be unpredictable when these are introduced, but I think it's exciting that people are exploring so many different avenues beyond traditional computing. General purpose computing. So I think, as I said, there's real scope to make radical changes here and look what comes beyond the traditional microprocessor. I think there's probably an interesting spectrum of approaches between machine learning and what we call a microprocessor at the moment, or executing general purpose programs assisted by machine learning. So I think there's a whole area yet to be explored in that space. And machine learning, I think we can expect orders of magnitude in terms of performance and efficiency gains over the next decade. Okay, so I think one of the challenges going forward is how we innovate and discover good solutions faster. And I think there are many challenges with performing computer architecture research in universities. So I just wanted to spend just 2 quick slides in this area. I think there's also opportunities. So I think the first is design space exploration. So in many ways, discovery really is a sort of human speed. And it's funny, really, for computer scientists, we use very few tools in computer architecture. And the tools really haven't changed for a long time. And I think there's considerable scope in trying to improve those tools, especially with the help of machine learning, so we can improve the speed at which we perform every stage of the sort of research pipeline. And I think the goal here should be high throughput computer architecture research. I think we can perhaps aim to do computer architecture research an order of magnitude faster if we had the right tools. So this is supporting every stage of research, from the initial idea to early results, to interpreting the results, to really understanding what changes need to be made after you've understood the results that you've got. All those stages, I think, could be accelerated considerably. But very much with the human designer, at least at the moment, at the heart of the loop, if you like. So a system receiving human feedback and perhaps nudging humans into finding better solutions, but at a much faster rate. The other thing, which leads me on to lowRISC and the lowRISC project, is the challenges of performing computer architecture research in an academic environment. I think there's a lack of scale, and I think this sort of limits the type of projects that we can do. There's also, this is what we thought about a lot 10 years ago when we started lowRISC, there's a problem in terms of access to knowledge and infrastructure. PhD students often spend a large amount of time building infrastructure to perform experiments, and this can be slow. Testing ideas is slow. You often don't know what the state of the art is because industry keeps it secret. And the transition of technology into industry can be slow because the complexity of the design that you've been working with is far less of that of an industry's design. And you've perhaps missed some really important trade-offs that industry don't make particularly public. Test chips are also beyond most UK academia now. Most academia, full stop, still some projects in the EU and US. Some of this, I think, also feeds into people and training. So we need greater numbers of people. I think we need to think about the attractiveness of the subject. So I think some subjects are pulling in a lot of people because I think there's a feeling there's low-hanging fruit there, that it's exciting, that there's people to collaborate with, that there's lots of information you can access easily. I'm not sure computer architecture always has that image. And I think finally, because of some of these challenges, sometimes we're not always looking in the right place. So there's a trade-off in terms of what type of research project you do to limit manage risk. I think there's a question, are we tackling the really big questions head on, or are we sort of looking for niches that we can handle, that we can work within, given the constraints of research in universities? So there were some of the questions I think that at least I was thinking about when we started lowRISC 10 years ago. So let me talk about the lowRISC story. So as I say, I think low risk, at least for me, was partly an experiment about how we could go about fixing some of these problems, and how we can undertake larger scale projects that can't be done within university, and then ultimately how we can give everybody access to well-documented foundational IP and industry quality and complexity designs. And also address some of the industry challenges, so help make the research that's undertaken at universities more relevant, transition ideas more quickly, and allow industry to focus at the cutting edge. And of course, the obvious question, or the question I think both Gavin and Alex posed was, can we take inspiration from open source software? And I think, so I suppose, and so can we take inspiration from open source software and do the same thing for hardware? And I think, so the challenge is not to, I mean, it's not to replace academic research, and it's not to replace the way things are done in industry. I think ultimately it's trying to bridge the two and allow both industry and academia to get something from this type of project. So lowRISC was started in 2014, so 10 years ago. I think Alex sent an email this morning saying that it's been 10 years since we came up, well, Simon came up with the name. And it was, as I say, started with Gavin and Alex, who are here, both here. I see Alex. Where's Gavin gone? Oh, hey, sorry. And Andy Hopper's, as I said, our chairman. And so Gavin and Google, initially the project was supported. It was actually run out of the lab. There was a very small team here working on an open source system on chip design. We started the company in 2014. As I say, the goal is really to look at how we could use open source hardware, open source techniques, and apply them to the hardware world. So it sounds easy. It's been done for software before, but it's never been done for hardware. And I think there's many reasons why that was true. I think it's harder. The scale of the projects that we wanted to undertake were large, and we needed people with industrial expertise. We needed to pay those people. Ultimately, we wanted to make chips, and making chips is expensive. We needed to have tools. We needed to pay for tools. So you need, I think you also have to do things. You tend to do things that the level of verification, for example, in the hardware world is very high. You only often get one chance to make a chip. So DV is very important and very time-consuming. These projects run over long periods as well. So lowRISC has been going 10 years. The OpenTitan project that I've been talking about is sort of 5 years in the making. So they're not things that you can do very quickly. You have to support these projects with proper funding, governance structures, legal documents, etc. So we really wanted to try and do this properly and at scale. Luckily, in 2018, the ideal project came along. We'd been talking to Google for some time, and Google and others set up the OpenTitan project. So this is a consortium of companies, and the focus here was the design of a secure microcontroller running a root of trust application effectively, so the design of a silicon root of trust. And the motivation was really safe commoditization, lower costs, also wanting to raise the bar for security. So from Google's point of view, or any of the companies involved, raising the bar for security in the tech industry in general is a good thing and benefits everybody. So it was the ideal project, really, for an experiment in open source hardware. Transparency and quality are also essential. So again, it was a good project for that reason. And flexibility too. So people are going to take this design, they're going to use it in a huge number of different use cases. So the fact that it's open and flexible and built to be flexible is a really positive thing. And as I said, security is sort of downside differentiator. You want to build these things, you want to build them really well, but they're not your core business. You just don't want them to go wrong. and it's advantageous for everybody to have good security. So if we can make this widely available to everybody, then that's a very positive thing. So OpenTitan is a collaborative engineering project. We have many industrial partners who contribute to the work, both through funding and through engineers and engineering time. As I said, to build an open source silicon root of trust. And so this is, so a root of trust, as I said, is really an application, provides key security services to a digital platform below the operating system level. So over 5 years, and with lots of hard work from people within the project, we built a very large project with many contributors and constructed this implementation of this open source root of trust. Actually, it's one of the world's most active, or the most active open source silicon project, and probably the largest open source hardware project there is in the world. So what is open? So we have everything from RISC-V processors, RTL for the crypto accelerators, all the I/O, verification IP, as I said, which is absolutely central, and firmware and software. So it's a complete system. And I'm not sure where else you'd look to see a complete computer system, actually, in an open form. So as I'll come back to, that has lots of advantages for academia. So racing forward, so after, as I say, after lots of hard work by many people in the OpenTitan project, we got chips last year, and thankfully they work. So that was a great milestone in February. And of course, the next milestone after chips is products. It's really great to be able to share that OpenTitan will be the security chip for Chromebooks going forward. So it's great to see this, delivering, I think, on our original aim in lowRISC, which was to make open source hardware a reality. So this is taking the idea of open source hardware and taking it all the way through to product, which is really great to be able to talk about. So in addition to that's the discrete chip. In addition to the discrete chip, we have integrated variants, and these are being adopted by Revos. So these will be on the corner of Revos is a company making high-performance server chips. Sort of, I think, pocket NVIDIA is the phrase, isn't it, that people are using. And OpenTitan will go in the corner of many of each of these chiplets as their sort of root of trust. And I really look forward to seeing many other use cases announced in the near future. So just to wrap up, so in terms of, and I think of lowRISC a little bit in terms of an experiment. So in terms of contributions, created a company, a center of excellence for secure chip design here in Cambridge. We're about 30 people, many of them based in Cambridge, with a team in Zurich as well. And we have there's a company called New AE that we acquired that does secure hardware, side channel analysis hardware in Canada. So I think this is a great resource for the country and academia. The OpenTitan project has delivered a high-quality silicon root of trust. As I say, it's great that academia and others have access to a full computer system, both hardware, software, firmware, lots of useful information, well documented. All the DV is there as well, so people can really see how industrial quality chip design is done. I think for a long time it's sort of been a secret, and hopefully this will help draw more people into the subject. I obviously think it's super interesting, but that's often hidden from people. So I suppose a generalization of OpenTitan is the Silicon Commons approach. So this what we want to have is a high-quality library of hardware components, well documented, available for openly and accessible for academia and for industry to use. And I think the story here is that I believe that the Silicon Commons will grow quickly. The recipe is a sort of well-tried one. I think once you sort of kick off these open source projects, then the open and collaborative nature pulls other people in. This, of course, improves the commons, pulling in more people. So I think the reinforcing the advantages and sort of accelerating growth. So I think hopefully the future is very bright for the Silicon Commons. So I hope we've succeeded in some of the challenges that makes computer architecture research hard or research into designing chips, and will help many people. I can see many virtuous cycles. So help support the quality and relevance of research by bringing these industrial quality designs into the public. Speed the adoption of research ideas. So this year there was an MPhil student who worked on bringing post-quantum crypto acceleration to our crypto accelerator. She was able to work on the actual OTBN hardware, propose improvements to it, discuss them with engineers at lowRISC, and then you can imagine this might be in a product in a couple of years. So I think it's given the student a fantastic opportunity, I think, but also this ability to transition research really quickly into products is valuable for companies too. As I say, the goal is to complement and support industry and academia. We're not trying to change the way everything is done to being open source. Oops. It's great, as I say, so OpenTitan's been out for a while now. You can go to GitHub and look at all the code. And it's been used in lots of papers, actually. Often with people generating or experimenting with new types of tool, perhaps verifying security properties, using formal methods. So we had the group at Oxford presented interesting work doing formal verification of a version of IBEX, the IBEX core, sort of fully proving its functionality. And then we've had many companies pick up designs that we've produced. So Microsoft picked up the IBEX core, extended it with Cherry extensions. But we know that IBEX and other parts of OpenTitan have appeared in many industrial designs since its release. So I think, just to summarize, I think it's one of the most exciting, and I know other people, independently, people said this to me outside. They thought it was the most exciting time to be involved in computer architecture, and I'd have to agree with them. I think if we can provide the next generation of architects greater access to knowledge and IP, that can only be a good thing, and encourage the next generation of architects into the field. I think there's a huge opportunity to build better tools to help us do research faster. I think the low-risk model is a super interesting one to sort of bridge between different companies and industry and academia. What I sometimes think about is, wouldn't it be great if there were many of these low-risk type entities or labs per university department? And going forward, I think this would be a great thing as the complexity of the solutions we're going to have to build increases, and having these centers of excellence and foundational IP, repositories of foundational IP across subjects, I think would be transformational. And also, I think would prepare for this machine learning assisted future that I suspect is coming very quickly. So last slide. So, as I say, a really exciting time for computer architecture. I think it's time to be disruptive. I'd love to talk about what computer architecture will look like in 2049 with you. I think echoing some of the points that Alistair made, I think PhD students are absolutely the lifeblood of the department. And we are very lucky to attract the very best. I think it's disastrous if we can't give those students that have been offered places to work in this area, in computer architecture and machine learning, when it is so important. I think there's huge opportunities if we can undertake computer architecture and machine learning research in Cambridge and the UK at the necessary scale. I don't think it's being done at the necessary scale at the moment. I just wanted to have one final slide, which was, I'm not sure if Eben is here. Is Eben here? I thought he was, no. Rosie's here, and others are from Raspberry Pi here. But after those initial meetings 17 years ago with Eben and others, it is surreal to see this. But it's another great example, I think, of how to share knowledge and innovate in new ways. And I love the fact that basically a conversation with a few of us in a room that basically went along the lines of, why can't we just blah, 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 has turned into such a phenomenon and a charity with a trading company with a $1 billion market capital. So it's a fantastic story. And yeah, so well done to Eben and the Raspberry Pi team. And thank you very much for listening. Thank you.